Welcome to this application spotlight on Raman imaging for carbon nanomaterials. My name is Fabian and I am the application specialist for Raman imaging here at Bruker Optics in Ettlingen, Germany. Today I'm going to show you how the spatial information from Raman mapping and imaging can improve your carbon material research, its application and also the fabrication. For that, I brought 3 different samples, starting from graphite. This graphite was deposited on silicon wafers for us to more easily analyze. A second sample, graphene CVD grown bilayer, but if that is really a bilayer, we have to check. And to complete the family of carbon materials, I also have carbon nanotubes deposited on a silicon wafer with special catalysts to make them grow nicely straight. For all the measurements, we will use the Raman Touch microscope with its great capabilities to perform large area mapping. To start, I will place the graphite sample under the microscope, will close the safety door and orientate myself towards the software and start the measurement. Come with me. Once we are here in our software, the Raman Imager, we can increase the illumination of the white light and see our graphite that is deposited on the silicon substrate. With our laser line approach, we can create a Raman image of 160 by 80 micrometers in only 1.5 minutes, making it easily accessible to image larger areas. If we start the measurement now, we will see the result here in this window. You can see that the full laser line, the information comes in at a time, so we multiplex our data collection by having 400 spectra recorded simultaneously, and with that having a fast imaging technology. If we use a lookup table with some color in it and integrate over one of the graphite bands, we will nicely see very quickly the distribution of the graphite. Here in this orange color, we have a lot of graphite. So here we are nicely in focus and image it. And here in these black areas, we only have the silicon substrate, giving us the information where the graphite is located. When we go back to the carbon spectrum, we will see distinct peaks in it. We have the D, the G, and the 2D band. From which vibrations they come from and what they really mean, we will see in the second sample, the graphene, where we go into these peaks in a little bit more detail. For this graphite sample here, it would be important to check the ratio of these two peaks because they are an indicator for the crystallinity of our material. So if we create now the ratio of the D to G peak, we will end up between 0 and 2 and see a new distribution in our image. The blackish area will be our silicon substrate, so there's no information for us. But here in orange and purple, we can see slight differences in the crystallinity of our sample. If we look at those two, so let's say the orange here in red and the purplish ones in green, we can see that the ratio is slightly different. It's not very significant, but we can already resolve such small differences by creating a quick ratio between those two. And if we would result in values between 0.1 and 0.3, we would have a highly crystalline graphite. But since we end up between 0.8 to 1, more or less, we have a medium crystallinity, and everything that would be above 1, you would end up with a more poorer crystallinity of the graphene. The graphite. Depending on your application, you want to have a certain crystallinity, and with this fast imaging technology, you can cover larger areas to see how homogeneously your annealing process worked and what is the ending crystallinity of your sample. So in the end, we can say that there are slight differences, but overall they are not very significant. So we don't have highlights with high and other highlights with low crystallinity. So overall, the production of this graphite was successful. In order to look at the Raman spectrum of the carbon material into more detail and to explain what these peaks really mean, I brought the second sample, the CVD grown bilayer graphene, that was transferred from its copper substrate to a glass slide and will be measured also with the line mode on the Raman Touch. I already prepared this measurement, so let's directly dive into the file. What we can see here is a Raman image of about 80 to 60 micrometer, also recorded on the Raman Touch with the line mode, giving us more than 100,000 spectra due to the high resolution of 200 nanometers. When we now select, similarly to before, something with color to see highlights, we can see that if we select this 2D band here, we can see highlights in certain areas of our image. So let's start and select one of those to create different spectra for the difference we see here in the image. If you would do the same now also with the G band up here, we can see that the one that was orange before is now not orange anymore. If we continue extracting additional spectra, something like this blue here and this orange here, we can create additional graphene spectra that show shifts, peak broadening, and different peak ratios. In these three that are extracted now, we are not seeing any deep peak that should be there. So if we assume there is something here, we can see again new highlights up in the spectrum. And if we can also assign a color to that, we see a very small peak here. So we can already say we have a high quality of this CVD grown graphene. These spectra we can export now into a new window to have them bigger. And with that, I will use these to explain where these peaks come from and what they can help us with our analysis. For that, I prepared a little presentation, so let's jump right into that PowerPoint. What we see here now are our extracted spectra, and they display what you will generally see in all graphitic materials, namely the D, G, and 2D band. Here in this high quality graphene sample, the G and 2D band is very prominent, and only for certain areas we could extract a very small D band. To explain these peaks, we have to look at the different vibrational patterns of graphene. The G peak on the one hand arises from in-plane vibrations, where carbon atoms vibrate in opposite directions, while both the D and 2D band come from ring breathing modes, and despite originating from a common vibrational mode, they exhibit different frequencies due to the electronic structure. Due to that, you will have this big shift in frequency between those two. The 2D band involves namely a two-phonon process. This results in this shift to higher wave numbers, whereas the D peak involves a single phonon scattering that is forbidden in normal graphene. This peak only appears through interaction with lattice defects and to create in that way a non-zero change in momentum. With that, we have this peak exclusively in very defective graphitic material, and in high quality ones, you should not see it as we do. If we look now at the two bands that are most prominent, the G and 2D one, you can use a ratiomeric analysis to extract the amount of layers. If you create the ratio between the intensity of the 2D peak towards the G peak, you will see for monolayers, you will have a value that is higher than 2. For B layers, you will have almost a 1-to-1 ratio, and for multi-layers, you will get values below 1. That way, you can easily color code your Raman image by creating this ratio and looking what values correspond to a certain color. So in that way, you can say everything that is higher than 2 becomes red, everything that's around 1 will be green, and everything below 1 will be blue. And you will have these three colors in your Raman image, and with that you can see how many layers you have in what position. However, we can also look more closely at the G band because there's more information in here. And the most obvious one will be the difference in intensity. So this sharp band at 1585 that comes from the sp2 bonded lattice has an increased intensity for multiple layers. So by just looking at the intensity of this peak, you can already get the information if you have mono, B, or multi-layers. It's not as sensitive as the ratiomeric approach, but for a quick assessment of the layers, this works very nicely. Here in this sample, the peak position is almost the same for all layers, but depending how you prepare your sample, you can also induce a peak shift in the monolayer graphene that will go to higher wavelengths, and with that, probing also the position of this peak will give you an indication of how many layers you have. If we shift now to the 2D band, we can also see differences between the different layers. The position clearly shifts with the increasing amount of layers. So in red, the monolayer is showing the lowest wave number, and the B and multilayer are shifted to higher wave numbers. Additionally to that position shift, you also have a broadening of the full width of maximum of the higher amounts of layer compared to a single layer of graphene. So you can also use the position and width of the 2D band to get a feeling for how many layers you are probing with your confocal volume or with the laser line. To cover all the peaks, we also have to look at the D band that is indicative for defects, as we learned in the beginning. And if you look at it, you also have a clear difference between high and low defect density, because basically if you have no defect, there won't be any peak. So if you probe the intensity around 1350 wave numbers, you have an indication for the amount of defects. You can also do here the ratiomeric approach and do the G to D ratio to have a more robust analysis method to compensate for baseline or any other effects that might come during your measurements at different positions in your sample. With that, we can now analyze 2D to G ratio for layers, the G intensity and position for the amount of layers, the 2D position and width for the amount of layers, and also the intensity of the D band for the amount of defects. With that, we have a very large toolbox that we can use to analyze our sample to the amount of detail we need for our analysis. We can now use all the information that is hidden in the Raman spectra of carbon materials. We can now go back to the Raman image of the B-layer graphene and see if we really have two layers deposited on our glass slide or if the CVD growing process was not good enough. Come with me. We are currently at the stage that we left before we went into the PowerPoint presentation. And from what we now know is that currently we have highlights where the graphene shows defects. So if we start now putting certain thresholds on our image, we can nicely see that along these cracks that we have, a lot of defects come in place, and also that a few of these, I would say, islands show highly defective graphene. So if we clean up our spectra a little bit and zoom in to this part, we can see that here is this defect. If we go to this one, we have it as well. In one of these darker areas, this band more or less vanishes since it is forbidden and only present in such defective carbon samples. We can nicely see how good the overall quality is. We can also use this line mode to average along one of these cracks to also see, yeah, we have here some defects that also look like along these cracks they are higher than on this more aerial distributed ones. More importantly now for our quality control of this B layer, how much B layer there really is. If you remember, this can be easily done by the intensity ratio of the 2D band with the G band. If we set now our borders between 0 and something around 3, we can see a distribution of different layers in our sample. From the values we are getting, so green and black, if there is some, would be multi-layer. Purple would be a B layer, because that would be around 1. And orange would be everything that is a monolayer. So multi-layer, B-layer, monolayer. With that, we can say our sample mostly consists out of monolayer. It has some B-layer islands where the CVD growing process worked sufficiently. And then we have a few chunky multi-layer bits that is shown here and here by the dark green black color. For a more precise determination of these ratios, we can also quickly perform a peak fitting where we can auto add two peaks, the G and the 2D. And if we fit our imaging data, so let's select all of the image. We can get the values of the amplitude, the width, and the position with higher precision by the fits that we performed. Let's quickly wait until all the pixels are peak fitted, and let us look at the newly created image. What we want to do now is calculate and divide amplitude 2, which is the 2D band, by amplitude 1, which is the G band. Select the same lookup table for comparison select thresholds between 0 and 2. And now we have a clear picture that, as we said beforehand, everything above 2 is monolayer. So all that's yellow whitish, everything that's bluish purple is a B layer. So most of these islands, and everything that is green and black is multi-layer. So here we have values above 2, around 1, and below 1. With that, the label of it being a CVD chrome B layer graphene is wrong because most of the area that we see here is a monolayer. With our fast imaging technology, we can even extend this measurement to bigger areas to truly confirm the inhomogeneity. But this fast measurement already showed us that this sample is not really useful if you rely on a B-layer sample. Until now, we talked about 2D material, graphene and graphite, and to finish this webinar off, we'll also look at carbon nanotubes. These had quite a hype a few years back, but still there are a lot of research going into those, using, for example, catalysts to grow them in straight lines and not having spaghetti-like carbon nanotubes. So we also use Raman imaging here to assess these tubes and also to analyze their properties and features. For that, I prepared a measurement as well, where we have a silicon substrate and carbon nanotubes on them, where we use our line imaging mode to cover a certain area and to see how they grow. Again, we use the laser line mode and image this 80 by 16 micrometer area. Carbon nanotubes are relatively weakly scattering, and if you have them just as powder or so on, they are extremely fragile, and here the laser line mode on these silicon substrate, but also if you have them in other conditions, really improves the minimization of sample damage, because with a laser point source, you easily break these nanotubes and destroy them. What you see in most of the spectra, due to the much better scattering efficiency, in this case of the silicon substrate, is the silicon peak here at 520 nanometers. If you zoom in where the D peak, the G peak should be, you have a relatively weak one, but you have one. If you use the line tool again and average across one of those tubes, you can easily get a strong signal to noise with a good quality of this peak. We've already talked about DG to D, the ratios and the meanings. Here, something new appears in these nanotubes, since it's not aerial, but more or less cubic. We have radial breathing modes. These radial breathing modes appear at the lower wave number range below 300 nanometers. Having this tube selected, we already see one of those breathing modes around 195 wave numbers. If we integrate now over this peak, we see that we highlight one, or let's say two, of these nanotubes. These radial breathing modes directly correspond to a certain diameter of the carbon nanotube. This means the higher wave number of the radial breathing modes, the shorter the diameter. So every nanotube that appears in this range will have a smaller diameter than all the nanotubes we can make visible in the lower radial breathing mode range. What we can do now is continue in this area and look for additional breathing modes, like for example here with the green one. If we integrate here around 179, 2, 3, more of these nanotubes are colored in green. If we also average along the nanotube, we can see a weak radial breathing mode at that position. When we continue now, we can see that if we are somewhere around here, this blue line appears in here by optimizing the threshold. We can also make that more visible. If we do that with all of the colors, we can minimize this background noise and see a line in here. If we look at the spectrum that we can get from here, we will see a strong breathing mode in that direction. We should be able to optimize our integration here, since this peak is a little bit broader, and highlight this mode a little bit more. We can also see some of these down here where the catalyst was and the nanotubes started growing. Maybe look for one more, maybe here. So you can see here a straight line and also here a straight line. I have to admit it's quite weak because the scattering signal is also quite weak, but through optimization, we should be able to make them visible. Again, a new breathing mode appeared around 130, giving it the biggest diameter of the four that we have here. So purple or pink has the biggest diameter and red would have the smallest diameter. In order to get a higher quality, one has to most likely spend more time here, average more to decrease the noise and to increase the signal quality of the radial breathing modes. But what you can see here is that not only the famously known G, D, and 2D bands can give you insights into your sample, also the special radial breathing modes of the carbon nanotubes help you analyze what you synthesized in the lab. With these findings, we are now at the end of our application spotlight, and I will thank all of you for joining in. If you need more information about the Raman Touch or about the analysis of carbon nanomaterials, check out our Bruker homepage and also our Bruker YouTube channel, where we have a lot of showcases and highlights of the application of the Raman microscopes that we have here at Bruker for different samples. Ciao!